Well, good afternoon, everyone. Welcome to our webinar on asbestos testing. It's great to see so many of you online. Probably there are a few more coming in as I'm speaking now. The purpose of today's webinar is to discuss the process for gaining accreditation for 5370, the new standard for asbestos identification in bulk samples. And I'll be discussing that. And then we're going to have a comparison of AS 4964 with, that's the previous standard, with 5370, which Carl Strautins is going to talk to. And also then we're going to have Richard Wilkinson discuss some differences with some issues with the fibre counting method. I'd like to take this opportunity to thank Carl and Richard for taking the time out from their busy schedules to help us today and provide the presentations. We're recording this session for future use, so please click the agreement. So my name's Neil Shepherd. I'm the Sector Manager of Life Sciences for NATA. Most of you will know me, I think. So I'm going to just briefly cover the process of gaining accreditation to 5370. And then, as I said, Richard will talk about air monitoring and reporting of fibres per field and fibres per mil. And then Carl Strautins will talk about a comparison between AS 5370 and AS 4964. So just looking at the current standard, the standard AS 4964, we will continue to offer accreditation to AS 4964, and you will have noticed the scopes of accreditation have been updated with the date there in brackets. That's been completed now. Applicant and accredited facilities are required to use the current standard 5370 unless a regulatory or client requirement to use 4964 is in place. So you do have the choice. We will continue accreditation to 4964, but you can move to 5370 when you wish. And just an overview of the process. We've sent out a couple of communications on that. So the first thing to do is obtain a copy of AS 5370, of course. You need to get that from Standards Australia or another authorised reseller. NATA doesn't provide copies of standards. And then review the AS 5370 against current practice in your laboratories and complete the implementation checklist, which was circulated. Then it's really standard NATA's practice after that. So complete the application for changes form, AEP 41.3, which can be downloaded from the website. Submit the completed forms and a copy of the in-house method for review in the normal process. And then facilities that are accredited to 4964 currently will assess you by desktop variation, which means we won't be making a visit to the facility. And then when the findings are addressed, then we'll grant the accreditation to 5370. Now, if you're an applicant facility, you will have to have an on-site visit to get the 5370.
So thank you, ladies and gentlemen. Today, this is predominantly about AS 4964 versus the new standard. However, I and Neil took this opportunity to ambush this meeting and just for TAs and facilities to run through some basic requirements of accreditation for asbestos air monitoring and fibre counting. It's always good to have a refresher, especially for TAs. There are things that come through the system that get flagged, and we don't normally get an opportunity to look at these issues. However, we're going to talk about a couple of things from different aspects of accreditation, and if there's any questions, more than happy to answer them in this forum or outside. But some of the things that come across our paths when we're talking about asbestos air monitoring and fibre counting. So Give me a second. First of all, so identified issues around about competency and sampling. So when we're auditing, what we're looking for is our training records up to date and present. Has experience been demonstrated and has the facility documented these things? Performance of in-house calibrations. Is there a manual that's easy to interpret? Are the facility across what needs to be done for their equipment to be fit for purpose? And are the staff across that and competent to undertake those tests? So the use of sampling equipment in the field. Are the consultants who are out there sampling understanding the parameters of where pumps need to be placed, the parameters of how pumps are placed, how equipment is set up, the desired flow rate to achieve certain volumes, and looking at flow rate variation criteria, obviously 10% for asbestos, for voiding samples. And field sheets and chains of custody, really critical that they're filled out properly. And if samples are being submitted to a laboratory, that there's an accompanying COC. So sample retention and archiving, again, really important. How are the samples being kept and how long do they need to be kept for? These are all the things that we need to be asking questions about as TAs and reviewing. And this is a very high level discussion. So, you know, nothing too complex in here, just the basics. So calibrations. In-house calibrations, metrological traceability, that's the cornerstone of our ISO 17025 accreditation. So soap bubble tube calibration and correction factor. Has it been calibrated sufficiently as glassware? And are we applying a correction factor when we're using the soap bubble tube? Obviously, our MU tells us that no measurements are absolute. So what is that uncertainty and how do we apply that when we're calculating the performance of our secondary flow meters? And if a calibration curve is required, is it accurate? And is it being used in the field by the consultants? So do pumps meet the flow rate variation criteria compensation? Can we check the variation compensation for a pump? Is that being checked? And what is the decision rule regarding acceptance criteria? If a pump cannot perform and demonstrate compensation checks, then it's not fit for purpose. And calibrations of stage verniers or calipers used to calculate effective filter areas. The guidance note for the membrane filter method quite clearly states that the stage verniers on your PCM microscope or calipers must be calibrated and be traceable to a standard. I know those EFAs, graticule and K-factor calcs, accurate and fit for purpose. And what about the manufacturer certs for our test slides, for our MPL HSE test slides? Can we verify their manufacturing specifications through the certificate of currency? So on to analysis. When we're sat down at facilities or we're training our people as tech assessors or in-house service providers, is a microscope setup protocol being reviewed? Low power scanning, high power scanning, rejection, acceptance criteria, and definition of countable fibers. You may think some of these things are really arbitrary, but recently we've had some TAs raise that these things have not been picked up at previous audits, and facilities are still in the dark about some of these real base issues. And the counting rules. What are the counting rules? What are the stopping rules? 100 fibers or 100 fields, minimum of 20 fields. And the criteria for analytical or field blank acceptance rejection criteria. And the cover slip thickness, all critical issues that affect the analysis of our slides, but something that we need to be paying diligence to in a laboratory setting. And the reporting of results. So manual and digital fiber concentration calculations. As we move into a brave new world, we're all using digital platforms. Some facilities will still be using paper. However, how are we calculating? Can a consultant, can a signatory, can a laboratory technician, somebody who releases results in a facility, calculate manually a concentration? I want to be able to see that somebody can do that. How are they verifying that the digital concentration calculator is accurate? And how is that digital fiber concentration calculator reacting when we change the parameters, when we shorten the volumes? Is it reviewing and increasing reporting limits as per we would of Table 3 and the associated documentation of the guidance note? So voiding samples in the field, voiding samples in the lab. What are those reasons? Are pumps being moved? Have pumps exceeded their flow rate variation criteria? Is the filter damage? Is the bleed into the margin? All these fine details. And the rounding rules, as I've just alluded to, per Table 3 of the guidance note. It's not just as simple as taking a volume of air and counting less than 10 fibers and reporting it as less than 0.01. That is not the criteria for the method. The method extends far beyond the clearance standard of 0.01 fibres per mil. How are we as an industry maintaining that people understand the standard, can read the standard and implement it properly? And the issuing and reissuing of reports. Are reports being issued to a satisfactory standard? And if a report needs reissuing, are we correctly annotating the document to capture a new version so we don't have duplicated data out there? And the reasons for that reissuing documented on the report. And most importantly, and the crux of why I really want to speak today, is the control of sampling. If we are a facility, a consultancy or a laboratory where we primarily send our consultants out into the field to conduct sampling in the field, how are we reviewing their performance? But more to the point, we know that there's a mechanism out there in the industry where some laboratories will take equipment and calibrate it for another consultancy. They will train people under their accreditation, and they will then take the samples and analyze them and report them of concentrations, with the key factor being the control of sampling. And this is most important for technical assessors. When we are out there, we need to be doubling down on, does the facility, which is undertaking such a process, have control of the sampling? So what does control of sampling mean? Does that mean handing the cowls to somebody and taking them back at the end of the day, then sending them an invoice? I think we're all selling ourselves short if that's where we're at. So these are the most critical points of today. And today was really a build up to this point. Is the provider of training for samplers deemed competent to do so? So is that person who's handing out training at a facility to consultants who don't have accreditation deemed competent? Do they have experience? Have they ever been into the field themselves? Are samplers being audited on an ongoing basis by the facility which has control of sampling? Are non-conformances being reported and actioned from these samplers in the field, and are they being retrained as an ongoing process? Can the facility demonstrate it is aware and has knowledge of all the sampling under its control on any given day? Personally, I run a team of 20 plus consultants. I know where everybody is on site and I know where they're all sampling and I know the scope of work. Now, if you can't do that as a facility, then we have a lack of control of sampling. Can you demonstrate that you intrinsically understand the work that's been undertaken under your accreditation? Is the equipment used in calibration under the said facility? Did you calibrate the equipment or did some other facility do it? If you're not accredited for calibration, then you can't calibrate anybody's equipment unless that sampling is under your facility and under your control. And is that equipment fit for purpose? How do you track that? How do you manage that? And most importantly, an airborne concentration cannot be issued if the sample volume cannot be verified as per the requirements of ISO 17025, the guidance note for the membrane filter method, and under NATA accreditation for volume measurement. If you cannot verify the volume and substantiate its validity, then fibres per field is all you can write. I've seen out there that people asterisk a report, which NATA has rejected a long time ago for air monitoring. There are mechanisms with NATA for various test methods for issuing reports that are non-NATA. However, that does not imply that if you don't know the volume, that you can't verify the volume, you can just simply make it up and issue it as non-NATA, implying that you understand what the volume is when you can't. So for airborne asbestos fibre concentrations, if the volume has not been verified, then there is no mechanism for issuing a concentration. I can't put more of a point on that. And that's all I've really got to say today. Mine was just a warm up to what comes next. Thank you for listening.
Good afternoon. AS 5370 is a new Australian standard for the sampling and qualitative identification of asbestos in bulk materials. It spans some 116 pages, which I have read all of it. And however, the true story lies beyond the pages and includes the dedication of volunteers within industry, government, and the scientific community, engaging in robust discussions and crafting a standard that effectively addresses Australia's asbestos challenge. While this is a consensus standard, it's not flawless and it never will be. But every sentence within the standard serves a purpose. It's been carefully considered and debated. Though not every aspect may be immediately clear, but when you consider many different scenarios, it's clear that this is the optimal solution. And while detection and reporting limits are debated, particularly with soil, and new technologies introduced, the fundamental question remains: how confident must we be in identifying asbestos fibres from other similar fibres? And if we report to lower limits of detection, does it really make any meaningful difference in the decision that needs to be made in assessing the probability of a health risk outcome? But perhaps that's a debate for another day. The key takeaway is that for the vast majority of cases, the new AS5370 standard and the old AS4964 standard will produce no meaningful difference in the reported result. The main changes include the introduction of electron microscopy and the allowance to use polarised light microscopy for additional asbestos varieties of actinolite, tremolite and anthopolite. However, those three varieties must be confirmed by electron microscopy, and there is no more reporting of unknown mineral fibres. These changes are aimed at resolving ambiguities in the previous standard, as certain asbestos types have overlapping refractive indices that make unequivocal identification difficult. The analytical sequence now in the Australian standard reinforces the importance of stereomicroscopy, where trace, or as it is now known as residual analysis, is only required for non-homogeneous samples where asbestos has not been identified. And there's also more comprehensive section on on-site sampling that overlaps with ISO 17020 inspection activities. So for some background in standards development, Australian standards undergo a revision process every 10 years to ensure that they remain current and relevant to the Australian economy, and it considers technological advancements and ongoing needs. As a general principle, Australian standards aim to adopt international standards unless there are compelling reasons not to. And this approach is intended to reduce barriers to trade and is part of Australia's commitment as part of the World Trade Organization. And this is where ISO 22262-1 was identified as the international equivalent standard. And we did an initial gap analysis and found that there was no compelling reason to reject it. The initial gap analysis was aimed to determine alignment with AS4964 and identify any major discrepancies that could render the document unworkable. The findings revealed that the scope of the standard was limited to commercial samples, which is inadequate for the broader Australian context, where we really needed a standard to include ores, soil, and naturally occurring asbestos. There were some minor discrepancies noted in the analytical criteria, with the ISO standard being slightly more rigorous, and facilities will need to map out in more detail the change in the new analytical criterion for the classification of the asbestos varieties. Other changes included different refractive index oils and higher temperature limits when disintegrating samples prior to analysis. And additionally, the Australian standard has the international standard has a more prescriptive approach. The Australian standard has a more prescriptive approach to trace analysis by using the 5 fibre rule on each slide to determine significant asbestos levels for reporting, where the ISO standard essentially is just said to take a pinch and put it on a slide and see if you could see any asbestiform fibres in there. So this method ensures consistency, unlike the ISO standard, which lacked the specificity and only required the reporting of identified asbestos in trace samples. Notably, AS4964 exclusively relies on polarised light microscopy as a single technique. And this is where the ISO standard introduces a new philosophy and allows for electron microscopy. The new Australian standard, in contrast to AS 4964, emphasises the use of multiple techniques for defining, characterising and identifying asbestos. And this is where we need to go back to the definition of asbestos and look at what each instrument tells us about the structure. So asbestos is defined as a silicate mineral in the serpentine and amphibole groups, crystallised in an asbestiform habit. And this is where the different techniques are employed to prove identity through observations of morphology, elemental composition, and its crystalline structure. And while polarised light microscopy is effective and cost efficient for most cases, electron microscopy is needed for complex samples such as naturally occurring asbestos and mining samples. This is where electron microscopy offers its advantages such as elemental composition analysis using energy dispersive X-ray spectroscopy and high magnification resolution of fibril structures that resolve the issues of morphology and crystallinity. To adapt to the Australian context, we've expanded the ISO standard to more than commercial samples. This includes dust, soils, and ores, aligning with the AS 4964 standard. Specifically for soil analysis, we've adjusted the sieve size from 10mm to 7mm to align with the WA guidelines as referenced in the National Environment Protection Measures, or the NEPM. The definitions of SMF and organic fibres have also been incorporated from the NATA accreditation criteria and carry over from AS 4964. The verification of trace analysis, now termed residual analysis, has been enhanced by implementing quantification of identified fibres to improve the accuracy of the reporting limits. There's also flowcharts from AS 4964 that have been refined to simplify and clarify the process. There's also an informative annex on measurement uncertainty that's been included to address test performance statistics. So don't be surprised if there may be a requirement in the future to estimate this. This is because measurement uncertainty is a requirement of ISO 17025. You might not think that uncertainty may not apply for a qualitative test, but think about any sort of medical test that you might have. I'm sure you'd want to know how accurate it is, so that you can make an informed decision on your health. And there's no difference here. And this is where we've provided references to start to understand how to calculate these test performance statistics, such as accuracy, sensitivity, specificity, and likelihood ratios. And these test performance statistics are useful in determining the overall error probability when multiple techniques are used. There's also been minor editorial changes that have been made to ensure compliance with the accreditation bodies. One item of note is that there's an omission in the current standard when translated from the ISO standard, and this specifically relates to morphology in clause 7.2.3.7.1, items C1 through to C5. So please keep this in mind when you're considering the standard, as it's currently under review, and I should anticipate that it'll be corrected shortly. So redefining trace analysis, this is one of the big changes. So the new standard redefines trace analysis, which is now called residual analysis, and this is done to prevent confusion between the new and the old standards. So the review during the AS 4964 trace analysis, we revealed that it may detect several magnitudes lower than the reporting limit, hence the focus in a more rigorous approach to determine if the reporting limit is exceeded. This approach is somewhat similar to the method used to calculate whether the reporting limit has been exceeded for soil analysis, with the exception that a residual weight of 5 milligrams is applied to a 22 by 22 millimetre area, which equates to about 0.01 milligrams per millimetre squared. And we use that measurand in looking for electron microscopy equivalents. So asbestos fibres are identified under the analytical technique and the dimensions are recorded, whether it's SEM, TEM or PLM. And the total fibre volume is calculated based on their dimensions, and then the density of the asbestos is applied to determine the total asbestos fibre weight. The concentration is then evaluated by comparing the assumed dust weight with the calculated fibre weight, and to then establish whether it's above or below the reporting limit on a weight per weight basis. The process is repeated with another slide, and if 2 slides yield concordant results, either above or below the reporting limit, the result is then reported accordingly. In cases of discordance, a 3rd slide is prepared and the result is based on the 2 concordant slides. The procedure is the same as in AS 4964, however, it incorporates a crude point counting criterion. So it's also important to note that AS 4964 incorrectly suggests that trace analysis under polarized light microscopy can accurately detect respirable fibres. And because of the limitations in dispersion staining for fibres less than 1 micron in width, this severely censors the true concentration of respirable fibres that only electron microscopy can reveal. And this is why PLM is not a valid method for a risk assessment, as it censors respirable fibres. For instance, how many fibres do you think you'd miss when conducting fibre counting using phase contrast microscopy compared to PLM? Because this would be a gross underestimate, and you'd never pass proficiency testing criteria during this method. And this is where only electron microscopy can detect respirable fibres, and it addresses the limitation in AS 4964, which inaccurately suggests that respirable fibres can be identified under trace analysis. So the same procedural framework is applied to all 3 analytical techniques to ensure consistency across the 3 methods. Another key aspect is that residual analysis is only mandatory if asbestos is not detected in non-homogeneous materials. Otherwise, it remains optional. And to make it very simple and clear, AS 5370 says the presence of asbestos fibres should not be reported in any form when results fall below the reporting limit. This approach may not align with the preferences of some organisations, particularly environmental protection agencies, which might request lower analytical limits and detection limits. However, what is more concerning is the attempt to make decisions based on these results below the reporting limit. Such results are inaccurate and lack sufficient confidence to make any reliable decision, especially at such low quantities. The Standards Committee had thoroughly investigated this issue and concluded that results below the reporting limit of 0.01% weight per weight are essentially meaningless. If lower detection limits are deemed necessary, a separate standard should be developed through the Standards Committee and developed for a specific purpose. This would require advanced techniques and rigorous scrutiny, especially regarding sampling areas. However, this already exists in the form of the NEPM, which acknowledges that 0.01% is still fit for purpose. This advice is critical, as over-detection and over-treatment can lead to significant psychological and financial burdens, which are often overlooked. We just think about the recent mulch issues earlier this year and put that into perspective. Therefore, any assessment should be part of a comprehensive conformity assessment to ISO 17020 accredited organisations, rather than relying solely on analytical results, which can be biased due to sampling limitations. So this was long debated, and simply if you report below the reporting limit, you don't comply with the standard and the results are not valid. So putting this more into context, with more advanced techniques that are being reduced, the significance of the stereo microscope should not be overlooked. In commercial materials, if the asbestos cannot be identified, then the stereo microscope is used initially, and then after any sample treatments to elicit fibres out of the matrix. If the amount of asbestos present is below the reporting limit, then the material cannot be classified as asbestos-containing material. This is because ACM, by definition, is a material that by its design incorporates asbestos into the commercial product. And there is no known material that contains less than 0.1% that meets the definition of ACM. So the reporting limit being set at 0.01, which is 1 magnitude lower and incorporates a level of uncertainty in quantification when compared to the reporting limit. Thus, there's inherent uncertainty built into the design and decision rule to minimise the risk of a false positive result to an acceptable level. Consequently, there's no need to pursue lower detection limits for ACM. And then when we look at soil, there's essentially no change in the process to soil analysis, except to emphasise that polarised light microscopy overlooks a significant population of respirable fibres. And in our review, we carefully considered the National Environment Protection Measures, and specifically referencing Volume 2, Clause 4.10, which accepts a reporting limit of 0.01%. So further consideration of uncertainty with regard to the reporting limit helps to minimise the risk of false positives when assessing asbestos presence at the health investigation level of 0.001% weight per weight for asbestos fines and free fibres. This ensures that the method remains compatible, and we've adjusted the sample screening as well to use a 7mm sieve instead of a 10mm sieve to align with the NEPM guidelines. And it's important to remember that the NEPM guidelines represents only a health investigation threshold, and that contamination exceeding this level doesn't necessarily mean that the material is unsafe, but indicates a need for further investigation and analysis. When we compare the gravimetric determination with the analytical method, it's generally less common to detect anything above the reporting limit through analytical means alone. And since the health investigation level can be reached through various methods, the analytical result isn't the sole determinant. And that's where there's a critical factor in deciding whether the health investigation level has been exceeded, relying on the gravimetric determination. As such, there was no justification for attempting lowered reporting limits, given the unreliable quantification at those levels due to sample heterogeneity and representativeness, which remains the largest sources of error. So in summary, the overall error in the process is primarily due to sampling variability, and any enhancements to analytical accuracy or uncertainty are overshadowed by the sampling and subsampling errors. And efforts to refine accuracy further would require substantial investment in time, resources, and funds and technology without yielding a more accurate or meaningful outcome. Therefore, the reporting limit remained at 0.01% weight per weight to ensure a balanced approach to reliability and practicality. Also remember the requirement of a decision rule under ISO 17025 that has also been duly considered and inherent within the new standard to minimise the risk of a false positive result. So consequently, the Australian Society, through Australian standards development process, has concluded that there is no need to pursue lower detection limits, and the standard is fit for purpose when considering the assessment of asbestos in soil. And looking at dust, there's been some ongoing debate regarding the use of dust on tape samples. The new Australian standard explicitly prohibits this sampling method, and in general, dust testing is not recommended except in specific circumstances where asbestos release is suspected under investigation. Historically, settled dust testing has been mentioned in older documents from the National Occupational Health and Safety Commission, particularly in the context of clearance inspections. However, it's essential to note that settled dust testing is not a verification method for clearance inspections and should not be used for this purpose. Again, there is the issue of polarised light microscopy failing to detect a significant proportion of respirable fibres. And that's where AS 5370 directs readers to refer to other standards that are valid for such analysis. Additionally, for these specific cases, more than 5 grams of dust is required to come to any meaningful result. And dust testing should not be used to imply significant contamination. If a substantial release of asbestos fibres has occurred, a cleanup would involve a visual assessment. And if no visible dust is present, then it indicates no meaningful contamination. And this is where such assessments are better suited to inspection activities under ISO 17022, where decisions are primarily based on the visual contamination observations rather than analytical methods. And analytical methods are not required for decisions regarding reoccupation following asbestos removal activities. So in summary, dust on tape sampling is not a valid method for AS 5370, particularly for clearance inspections. So in conclusion, the new Australian standard AS 5370 is a modification of ISO 22262-1 and is designed to facilitate the testing of non-commercial samples. AS5370 should be seen as a screening test to determine whether the hazard of asbestos is present at a level of significance that requires further assessment. It is not intended for or fit for purpose in conducting a probability analysis or risk assessment. The correct interpretation is that because it has been identified according to AS5370, a risk assessment or probability analysis is required and by some other means. The standard is aligned internationally and allows facilities to now identify actinolite, tremolite and anthopolite instead of reporting unknown mineral fibres. However, these other fibres need to be confirmed through the new techniques of electron microscopy, and this formalises the confirmatory method that was previously included in AS4964. And it also emphasises the reporting limits that were already in existence for AS4964 to prevent over-detection. And while the transition may require initial investment, the long-term benefits are significant, and policymakers should consider adopting this standard and understand the rationale behind its design. Thank you.